Hello everyone. In this video, we're going to be taking a look at how to find the area between a couple graphs. So what I'd like to do is just reason through why this works. And then after we do that, I want to take a look at a couple examples, just putting this to use. So why don't we start with what we already know. So in our coordinate plane, let's say we have the graph of a function f of x. And it doesn't matter what this looks like. So let's just say we have this nice curve, and then this is the graph of y is equal to f of x. And then let's look at a specific interval from a, and we'll go up to here to b. Now, what we already know is that if we take the definite integral from a to b of this function f of x times dx, we know that this is going to give us the area underneath this curve to the x-axis, and then in between these two vertical lines, x is equal to a and x is equal to b. Now, following that same logic, let's say we had another function, and then let's say this one just looks like this. Let's give this one a different name. Let's call this one g of x. Now, if I wanted to know the area underneath g of x, we know that we would do the definite integral from a to b of our function g of x times dx. So the first integral, this is going to give me the area in between the blue graph and my x-axis. And then the second one in red, that's going to be the area underneath g of x to the x-axis. But let's say we wanted to find the area of this region in between the two graphs. Now, using some pretty basic geometry ideas, if I take the area underneath my graph of f of x, that gives me the entire area here. And then if I take away the area that's underneath my graph of g of x, that should give me just the area that's in between them. So if I subtract these two definite integrals, I should end up with that area in between the two graphs. Now, we can actually work with this expression a little bit and make it a little simpler, just following some of our properties of integrals. So we can actually bring that together into a single integral. Since the bounds are the same, we can do the definite integral from a to b. And then on the inside, we're subtracting, so we have f of x minus g of x, and then here we only need one d of x. So this little formula gives us a way that we can find the area in between two functions. Now, a couple things about this. Just based on the picture I have, this logic will hold true as long as f of x is greater than g of x. So on this interval, for every x value in here, the y value for f of x is bigger than the y value for g of x. So I can use this logic. Let's say that somewhere in the interval, maybe it's switched. So maybe instead our graph of f of x curved down and we came down like this. Well, what I would have to do is I would actually have to switch at this point, whatever that happens to be. I just labeled this C. So I would actually have to split that up. And for the first part, I would be doing f of x minus g of x. But as soon as I got to this point, because now f of x is below g of x, I would actually have to do g of x minus f of x. So it's really important to note that we always want to do the bigger function minus the smaller one. And if we have to do multiple integrals, that's totally fine. Another thing that we can note about this is that this formula where we take the bigger function minus the smaller one, this also does work regardless if our two functions are above the x-axis or below or a combination of the two. So just to show you what I mean, let's say I have a function that part of it starts above the x-axis and then it goes down below, and I'm going to label this as h of x. Well, now at this point here, let's say that's D. So if I want to find the area in between my graph of g of x and the graph of h of x, So up until this point D, so g of x is bigger, so take the area underneath the bigger one, subtract the area underneath the smaller one. That's what we had in the first time around. But now once I get to this point D, h of x is below the x-axis. However, this is still going to work out just fine because when I take the integral of h of x, if it's below the x-axis, all this area has a negative value associated with it. So underneath the graph of g of x, this is positive area, and then I'm going to be subtracting a negative area, so the double negatives cancel out, and I end up adding this area on, which is exactly what we want to do. All right, so now that we have a general understanding of how to find the area between two graphs, let's take a look at a couple examples just to put this to use. So the first example here, it says find the area of the region enclosed by the graphs of f of x is equal to e to the x, so our exponential, and g of x is equal to the square root of x. And then we're going to put some bounds on this. We're going to be looking at in between the vertical lines x is equal to 0 and x is equal to 1. Okay, so this is a pretty small interval. However, it is still a very good habit to get into to sketch this out so you can take a look at the situation and see what you want to do. So let's put a couple axes in here, and we are just going from 0 to 1. So along the x-axis, I'm just going to mark that value of 1. And now let's take a look to see what our graphs are going to look like. So the first one, f of x is equal to e to the x. So I'm just going to plot a couple points and then connect those together. So at 0, this has a value of 1. So e to the 0 power is 1. And then at 1, e to the first, that's going to end up being about 2.71 if we take a look at the decimal value. So just estimating somewhere around here. And then this is an exponential function, so we're going to have a nice smooth curve up to that point. Now for our second one, g of x is equal to the square root of x. At 0, the square root of 0 is 0. And then at 1, the square root of 1 is 1, so we're here. And the square root has a little bit of a curve to it, so we're going to sketch it out like this. And we are just stopping at 1, so I'm going to get rid of the little tail here. And then the other parts we had were the vertical lines at x is equal to 0, so that's this y-axis. And then our other bound, we're going to stop here at the vertical line of x is equal to 1. So in between these two graphs, this is the area that we want to take a look at. So moving along our x-axis, the formula that we developed, just to write that down again, so we have the integral from a to b are two bounds, and then we're going to take the greater function f of x, and we're going to subtract the smaller one g of x and times d of x. So essentially what we're doing is as I move along the x-axis, we're breaking this up into smaller and smaller pieces. So another way that we can phrase this is I want to find the area in between these two graphs by partitioning the x-axis. So essentially we're creating little rectangles, little vertical rectangles in between these two graphs. We're finding the area of each of these rectangles, and then we're adding those together, which is a Riemann sum, which we know that we can find with an integral. So everything we have here checks out. So f of x, this is greater than g of x for our entire interval. So we can just use our formula. So let's plug everything in. So we have the integral, and then our bounds are from 0 to 1. And then our two functions, we have e to the x, and then we're going to subtract the square root of x, and times dx. So using our properties of integrals, we're going to split that up over that subtraction. So we'll do the integral from 0 to 1 of e to the x dx, and we'll subtract the integral from 0 to 1 of the square root of x times dx. And remember, the square root of x, this is the same as x to the 1/2 power. So using our antiderivative rules, the antiderivative of e to the x, that just stays the same. And then for our second one here, this is x to the 1/2. So we have our minus sign. And then this is going to be 2/3 x to the 3/2 power. And then this whole thing, we're going to evaluate this from 0 to 1. And let's see what that's going to give us. So if we plug in 1, that's going to be e, and then minus 2/3. If we plug in 1 here, 1 to the 3/2 power just stays as 1. And then from that, we're going to subtract if we plug in 0. So if we plug in 0, e to the 0 power is 1. And then the second term, this whole thing will become 0. So we have e minus 2/3 minus another 1. So that 1 is like 3/3. So in total, we end up with e minus 5/3. And that's our final answer here. So the area in between these two graphs, between f of x and g of x, the area is equal to e minus 5/3. And just to think about an approximation for this, e is about 2.7, 5/3, that's about 1.6. So we're looking at an area somewhere around 1.1 square units. All right, now let's take a look at a second example. And this one is slightly different. So this one says find the area of the region enclosed by the graphs of f of x is equal to 10x minus x squared, and g of x is equal to 3x minus 8. So the one thing that's different about this problem is it's not giving us any left and right bounds. So it's not giving us any vertical lines that are also enclosing this region. So instead, what we have to do is we have to find where these two graphs intersect. And I'm going to start with that before I sketch the graph, just so I know what sort of range I'm looking at. So if I want to find out where these intersect, we can take the two graphs, the two functions, we can set them equal to each other, and when we solve that for x, that's going to give us our 2 points. So let's take a look here. We have 10x minus x squared, and let's set that equal to 3x minus 8. So we do have an x squared, so that means it's a quadratic. So we want to move everything over to one side of the equal sign. And since it's negative, I'm going to move everything over to the right-hand side, just so that ends up being positive. So we have a positive x squared. If I subtract 10x, that's going to be negative 7x, and then the minus 8. And I believe we should be able to factor this. So two numbers that multiply to negative 8, but add to negative 7. That's going to be x minus 8, and then x plus 1. So our two x values, we have x is equal to 8, and x is equal to negative 1. So at those two x values, that's where these two graphs are going to intersect. Now, right now, I'm not overly concerned about what the exact points are, just because I wanted to know my left and my right bounds, because that's going to help me set up my integral. And while we're at it, why don't we just sketch this out to see what we're working with. So the first one is a quadratic, and then the second one is just linear. And we're going from negative 1 to 8. And I'm just going to do a real simple sketch here. All right, so for the first one, it's a quadratic. And let's just take a look to see where this crosses the x-axis. So f of x, I'm going to factor out an x from both of those. And that's going to leave me with 10 minus x. So what this tells me then is it crosses the x-axis at 0. And then it also crosses the x-axis at 10. So that means the vertex of this parabola is going to be right in the middle at 5. So if we plug in 5 to this, it's going to be 5 times 5. So the maximum here is going to be up at 25. So we have a parabola that looks something like this. And again, this is just a real simple sketch because my whole goal with this is just to give myself an understanding of what I'm working with. You know, the second one, we have g of x is equal to 3x minus 8. So that's linear. It has a y-intercept of -8. So we'll just kind of estimate that out. So let's say -10 is here, so not quite. So we'll go like here at -8. And then let's just think about where this crosses the x-axis. So if this was set equal to 0, then solving for x, we end up with 8/3. So that is 2 2/3. So a little bit over halfway to 5 here. So let's say about there. And now let's connect those together and we can see what we're working with. So connecting together those points to make our line. And taking a look at my graph, I actually need to extend this out a little bit because our other point of intersection is actually going to be at -1. So I need to extend out my parabola to this point of intersection, like so. So now our 2 points of intersection, we have here, this is going to be at -1. And then the other point of intersection that we found, this will be at 8. And then the area that we want to find is in between these two graphs. Now taking a look at the sketch we did, we can see that on this entire interval from -1 to 8, the graph of f of x is greater than the graph of g of x. So we can simply use our little formula. So we're going to do the integral from -1 to 8. So those are the bounds that we found by setting these two equal to each other. So we could see these 2 points of intersection. And then we're going to be doing f of x minus g of x times dx, because f of x is greater than g of x on this entire interval. So now the integral from -1 to 8, and then f of x was 10x minus x squared, and g of x, I'm going to put this in parentheses so we know to distribute the negative. And here we can do a little bit of simplifying. So we have our integral from -1 to 8. And let's see, we have 10x minus 3x. And I am going to put the negative x squared first. So 10x minus 3x, that's going to be plus 7x. And then we have the minus 8. Now we can go through and use our normal antiderivative rules for each of these terms. Technically, we would be splitting this up into 3 separate integrals. But let's see what we get. So for the first one, we have our negative. That's going to be x cubed over 3. The second one, we need to divide by 2 to make sure that simplifies. So that's going to be x squared, and then 7/2 out front. And then our last one, we have negative 8x. And we're going to evaluate this from -1 to 8. And now let me just scroll down a little bit to give myself some room so that we can plug in these two values and see what we end up with. So for the first one, if we plug in 8, it's going to be negative 8 cubed over 3. And then we have plus 7/2 times 8 squared, and then minus 8 times 8. And from that, we're going to subtract, plugging in the second one. So that's going to be negative, and then -1 cubed over 3, plus 7/2 times -1 squared, and lastly, -8 times -1. And to do some simplifying before we figure out our final answer, 8 cubed is going to be 512. Our second term, 8 squared is 64. And then if I divide that by 2, we'll have 7 times 32. And then here, 8 times 8, we have negative 64. In our second set of parentheses, -1 cubed is going to be -1. That will cancel out with this negative. So that is 1/3. -1 squared is positive 1, so we have plus 7/2. And our last one here, so this will be, actually, so we have minus a -8, so this should be plus 8 throughout our integral, which will just change a couple things. So this will be positive 8 plus 8, and then this will be positive 64. And then over here, we'll have a positive 8 times negative 1. So now that's going to be minus 8. And now if we figure out our grand total for this, we end up with 243 over 2, or as a decimal, that is 121.5. So here, our area in between these two graphs is 121.5 square units. So that's how we use calculus to find the area in between two graphs. In the first example we did, we were using vertical lines to help us enclose our region. And in the second example, we had the additional step of having to figure out the points of intersection between our two functions so that we knew the bounds that we were going to use for our integral. But regardless, the main idea here is we're finding the area underneath the greater function, and then we're subtracting the area underneath the lesser function on a given interval, and that's going to give us the area in between the two graphs.